Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be counting with recursions. So what is a recursion? It is a formula for a sequence, A0, A1, A2. It's a way of defining the nth term of the sequence based on an initial condition or maybe several initial conditions, where you declare what A0, A1, A2 up to AR are for some finite number R. And then a recursion, which is a formula for A sub n plus 1 in terms of all the previous values A0 up to AN. So a recursion is sort of similar to the idea of induction, where we start at the base case and then we go up the rungs of the ladder to prove a statement for all n. Here, we're defining a sequence by starting with the first few values and then saying how to get from one value to the next or from previous values to the next. So here's a very simple example of a recursive formula for a sequence that we all know and love. If we define a sub 0 to be 0, if that's our initial condition, and then for all n, a sub n plus 1 equals a sub n plus 1, what that means is that, well, we know a sub 0 equals 0, and we can figure out using this recursion what a1 is. A1 is A0 plus 1, which is A0 plus 1, which means you take the previous number and you add 1 to it to get to the next number. So then the next number will be 2, and the number after that will be 3, and 4, and 5, and so on. So this is just the counting sequence, 0, 1, 2, 3, 4, dot, dot, dot. The explicit formula for this sequence is not recursive. Recursive tells you how to get from previous values to the next values. Explicit means you plug in n into an actual formula and you get your nth value. The explicit formula in this case is, of course, a sub n equals n. Now let's revisit the factorial, which is something we used to define as the product of the numbers 1 times 2 times 3 dot 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 up to n. Now whenever you see a dot 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 in mathematics, secretly there's a recursion hiding behind it. So here's the formal way of defining n factorial recursively. Use the initial condition where, let's say, f sub 0 equals 1. We'll use f for factorial. We don't need to use a for our sequence, could be any letter of the alphabet. So say f sub 0 equals 1. That's declaring that 0 factorial is 1. And then we define f sub n plus 1 to be n plus 1 times f sub n. So let's see how this plays out. If we unwind the recursion, we start at our initial condition of 1. And then on the first step, we multiply by 1 and we get 1 again. Then on our second step, we multiply by 2 and we get 2. On our third step, we multiply the previous answer, 2, by 3 and we get 6. And on the fourth step, we multiply by 4. 6 times 4 is 24. So you see, we're always multiplying by the next number to get the next factorial, and that's an alternative way of defining the factorial sequence. The explicit formula, of course, is just f sub n equals n factorial. Now let's look at another sequence that we're already familiar with, the powers of 2. This is where b sub n equals 2 to the n. So we're looking for a recursive formula for 2 to the n. In this case, the initial condition will be b sub 0 equals 1, and the recursion is that to get from one step to the next, you double it. So b sub n plus 1 equals 2 times b sub n. So that's another example of a recursively defined sequence that we also have an explicit formula for. Now notice we can also write b sub n equals 2 b sub n minus 1 for n at least 1 if you want. As long as you index your n correctly, you don't have to do n plus 1 in terms of n, you can also do n in terms of n minus 1. It's just a different way of writing the same thing. So now let's talk about solving recursions. Say we were given just the recursion for the 2-power sequence b on the previous slide, and we wanted to find an explicit formula for it. Let's say we want to prove that if b0 equals 1 and bn plus 1 equals 2 times b sub n, then b sub n has to be equal to 2 to the n for all n. So for a well-defined recursion like this, to prove it has some explicit formula, you want to use induction. To proceed by induction, the base case matches the initial conditions. So you want to check that for n equals 0, we have b sub n equals 2 to the n, while b sub 0 is given to be 1 by the initial condition, and that is 2 to the 0. For the induction step, you want to let k be greater than or equal to 0 and assume that the statement is true for k, so we want to assume that bk equals 2 to the k. Then we want to prove that bk plus 1 is 2 to the k plus 1, and so we use the recursion here in the inductive step. bk plus 1 is 2 times b sub k by the definition of our recursion, which by our assumption in the induction step is 2 times 2 to the k, and that's 2 to the k plus 1, and so that's what we wanted. So in general, here's how we solve a recursion. The first step is to guess an explicit formula. Once you write out the first few values, maybe you'll have a guess for what the nth term might be, but then you want to prove that your recursion actually gives you that. The next step is going to be showing that this f sub n satisfies all the initial conditions, like f of 0 equals a0, or if you have more initial conditions, you have to check all of them. But there's only a finite number of them, so you can just compute them. And the third step is to show that f of n satisfies the same recursive formula as a sub n does, because these two steps here give you the base case and induction step of an induction proof, and so you know that your explicit formula was correct. So let's use these three steps in an example here. Say we're given a recursive sequence defined as follows. The initial condition is a0 equals 2, and the recursion is a sub n plus 1 equals 2a sub n minus 1. So to get to the next number of the sequence, you double your previous one and subtract 1. So let's start at 2 here, that's our initial condition. And then we double 2 and subtract 1, and we get to 3. We take 3 times 2 is 6 and subtract 1, we get to 5. 5 times 2 is 10, subtract 1, we get to 9. 9 times 2 is 18, subtract 1, we get to 17. And 17 times 2 is 34, subtract 1, we get to 33. Those are the first few elements of our sequence, and we see that the recursion does uniquely define every element of the sequence. We can go all the way out. Let's try to find an explicit formula for this sequence. 2, 3, 5, 9, 17, 33 may not look familiar until you subtract 1 from them all. So compare this sequence to the doubling sequence 1, 2, 4, 8, 16, 32. That's formed by adding 1 to the powers of 2. So our guess for step 1 is we're going to guess that a sub n equals 2 to the n plus 1. So this 2 to the n plus 1 is our explicit formula f of n. So now with that guess, for the initial conditions, we want to check that a0 equals 2 to the 0 plus 1. Well, we're given that a0 equals 2 and 2 to the 0 plus 1 is actually 1 plus 1, which is 2. And to check that 2 to the n plus 1 satisfies this recursion, you want to plug it in on the right-hand side and see if we get the right thing on the left-hand side. So let's plug in 2 to the n plus 1 into 2an minus 1 here. So 2an minus 1 should be 2 times 2 to the n plus 1 minus 1. And then if you expand this out, we get 2 to the n plus 1 from these two terms, and then 2 minus 1 is just plus 1. So we get 2 to the n plus 1, which is exactly what we think a sub n plus 1 should be. And so our explicit formula guess does satisfy this recursion, and so we have what we wanted. If we wanted, we could wrap all this computation into an induction proof, but we don't have to because it's always the same steps every time when it comes to checking that an explicit formula satisfies a recursion. Let's look at a depth 2 recursion, and this is a very famous recursion called the Fibonacci numbers. The initial conditions are f0 equals 0 and f1 equals 1. We need 2 initial conditions to get off the ground. And the recursion is f sub n plus 1 equals f sub n plus f sub n minus 1. So each number is the sum of the previous 2 numbers, and notice I had to put n greater than or equal to 1 just so that n minus 1 is always defined here. So the first few values, you start with the initial conditions 0 and 1, and then each number is the sum of the previous 2. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, 5 plus 8 is 13. This keeps going off to infinity. The initial values matter very much in this case. Here's another example where we can use the same recursion. Each number is the sum of the previous 2 and get an entirely different sequence of numbers. Say we start with 1 and 3 instead of 0 and 1. Well, now the sum of 1 and 3 is 4, and then 3 plus 4 is 7, and 4 plus 7 is 11. We get 18, 29, 47, 76. None of these numbers appear in this sequence. Sometimes there's overlap just from coincidence, but it's a very different sequence in general. So the initial conditions matter a lot, and it is important that we have 2 initial conditions because both of those numbers determine what's going to happen for the rest of the sequence. Now here's a magical formula. If you look at the Fibonacci numbers, it's actually very hard to guess an explicit formula for it. But actually, there is an explicit formula. Now how you would come up with this formula, we're going to talk about in later sections of the book and in later videos. But for now, what you could do is once you do guess this formula, somehow, which Binet did, then you can show that it is the nth Fibonacci number by just showing it satisfies the initial conditions. So we plug in n equals 0 and n equals 1 into the formula on the right here. And then we show that it satisfies the recursion. You plug in n plus 1, you plug in n, you plug in n minus 1, and we show that this equality actually holds for this formula. And in the textbook, we do check that this satisfies the recursion. Now, how are recursions used in combinatorics? So let's bring it back to a counting problem. How many binary sequences of length 8 have no 2 consecutive ones? Now, this restriction of having no 2 consecutive ones is actually not very easy to work with directly using chooses or any of the methods that we've done for binary sequences so far. Instead, we want to use recursion. So if you start listing the first few values, let's list them by length. So if you have length 0, there's only one empty sequence, and so there's one such sequence of length 0. For length 1, you have the sequence 0 and the sequence 1, so there's two sequences. Neither of those have two consecutive ones. They're both okay. For length 2, we have all the binary sequences except for 1, 1. We're not allowed two 1s next to each other, so there are only 3 binary sequences satisfying this condition. For length 3, now we can have 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So if we only have 1 or no 1s, we're okay. If we have two 1s, we can put them apart, right? We can't have them together, but they can go in the first and third position. So there's 5 in that case. For 4, if you carefully list them all out, there's 8 of them. And now we might see something familiar. 1, 2, 3, 5, 8. These are Fibonacci numbers. And so maybe the next one is 13. But why are they Fibonacci? If your binary sequence ends in 0, then the first 3 can be any valid sequence of length 3 that avoids two 1s, because this 0 at the end isn't going to make two consecutive 1s, so it's fine to put at the end of any sequence. But what about the ones that end in 1? Well, the thing about the ones that end in 1 is they can't end in two 1s, so they have to end in 0, 1. But then once they end in 0, 1, now you have any sequence of length 2 that you want that satisfies the conditions. So the next 3 down here are formed by taking the 3 sequences of length 2 and adding 0, 1 on the end of them. And so indeed, we have 5 plus 3 possibilities for a total of 8 for 4. So if a sub n is the number of these sequences of length n, then here's our combinatorial argument for why a sub n satisfies the Fibonacci recurrence. Each sequence of length n can either end in 0, in which case there's a sub n minus 1 possibilities for the first n minus 1 digits, or it can end in 1, but then it has to end in 0, 1 because it can't end in 1, 1, and then you have a sub n minus 2 possibilities for the previous n minus 2 entries. And so a sub n does equal a sub n minus 1 plus a sub n minus 2, which means every element of this sequence is the sum of the two numbers before it. Once you realize this, then answering this combinatorics question becomes very efficient. Even if you don't know an explicit formula for the Fibonacci numbers, you can still just unwind the recursion very quickly. Make a little table here of n and a sub n, and we want length 8, so we make n go out to 8, and we start with our initial values of 1 and 2 that we computed by hand. And then each number is the sum of the previous two, so we get 1, 2, 3, 5, 8, 13, 21, 34, 55, and we're done. And so there are 55 possible sequences of length 8 that have no two consecutive ones. So now you try how many ternary sequences, meaning they have 0s, 1s, and 2s, of length 5 do not have any two consecutive 2s. That's all for today, and we'll see you next time.